Large portions of the planet's surface lie far below the ocean, forming an immense landscape of plains, ridges, plateaus, and trenches that extend across every major basin. These structures create the large-scale geometry of the seafloor, shaping how the ocean floor is organized across the globe. From broad abyssal plains to long ridge systems and deep trench corridors, the seafloor reveals a complex arrangement of topographic forms distributed across the world's oceans. Abyssal plains occupy extensive portions of the global ocean floor across the Atlantic, Indian, and Pacific basins. These sediment-covered surfaces form broad, low-relief expanses that extend across large central areas of many oceanic basins. In the Atlantic Ocean, abyssal plains are widely distributed on both sides of the Mid-Atlantic Ridge, spanning significant portions of the western and eastern basin floors. Comparable plains are present in the Indian Ocean, particularly across the Arabian Basin and the central Indian Basin. The Pacific Ocean contains numerous abyssal plains, though their spatial continuity varies across different sectors of the basin floor. Large sediment-covered regions are present in the North Pacific and South Pacific, separated by elevated features and ridges that segment the basin into distinct topographic compartments. Southern ocean basins also include abyssal plain regions, especially in sectors adjacent to continental margins. Abyssal plains are typically located between continental rises and mid-ocean ridge systems. Many of these plains extend over thousands of square kilometers, forming some of the most laterally continuous surfaces on Earth. Basin floors characterized by thick sediment cover are commonly associated with these plains, creating wide areas of relatively uniform topography. Global mapping surveys indicate that abyssal plains represent a substantial fraction of the deep ocean floor. Their distribution reflects the broad spatial arrangement of ocean basins rather than isolated occurrences. Across multiple oceans, these plains contribute to the large-scale organization of seafloor topographic features. Ocean basin floors cover vast continuous areas across the global seafloor. Large portions of the Atlantic, Pacific, and Indian Oceans consist of broad sediment-covered surfaces extending between continental margins and mid-ocean ridge systems. These basin floors form expansive regions of relatively uniform topography at the scale of ocean basins. Individual abyssal plains often span hundreds of thousands of square kilometers. In some basins, contiguous sedimented surfaces extend across multi-million square kilometer areas without major interruption by elevated relief. The North Atlantic Basin floor includes extensive plains west and east of the Central Ridge System. Comparable large-scale surfaces are present across central sectors of the Indian Ocean. In the Pacific Ocean, basin floor surfaces occupy substantial fractions of both northern and southern regions, though their continuity varies due to intercepting ridges and fracture zones. Even where segmentation occurs, the cumulative surface area of sediment-covered basin floors remains extensive. Southern high-latitude basins also contain broad plains distributed between continental rises and ridge structures. Globally, basin floor surfaces represent one of the largest geomorphic domains on Earth. Their total area constitutes a significant portion of the oceanic crystal surface. When viewed at planetary scale, sediment-covered expanses define much of the horizontal extent of deep ocean topography. The lateral scale of these basin floors exceeds that of most continental lowland regions. Across multiple ocean basins, these surfaces create wide fields of minimal gradient and broad spatial continuity, forming a dominant component of seafloor topographic features. Sediment-covered flat regions form extensive components of many ocean basin floors. These areas are characterized by broad surfaces with minimal topographic variation at regional scales. Fine-grained sediments mantle underlying oceanic crust, producing laterally continuous plains across large portions of the seafloor. Abyssal plains represent the most expansive examples of these sedimented surfaces. They occur in the Atlantic, Indian, and Pacific Oceans, often occupying central and distal sectors of ocean basins. In several basins, sediment thickness is sufficient to obscure smaller irregularities in the underlying crystal structure. The resulting topography appears smooth when mapped using large-scale bathymetric surveys. Sediment-covered regions commonly extend outward from continental rises toward mid-ocean ridge systems. In many cases, these plains form uninterrupted expanses spanning hundreds of kilometers. Fracture zones and isolated volcanic features may locally interrupt continuity, yet broad sectors remain comparatively uniform in gradient. The areal coverage of sedimented flat regions varies among ocean basins. The Atlantic Basin includes wide, continuous plains on both sides of its central ridge system. Portions of the Indian Ocean display similar expanses across its central and eastern basins. The Pacific Ocean contains multiple large plains, separated by elevated ridge and plateau structures, while still maintaining substantial cumulative surface area of sediment-covered terrain. At planetary scale, these flat regions constitute a significant fraction of deep ocean topography. Their distribution across multiple basins establishes sedimented plains as a dominant morphological element of the global seafloor. Transitions between abyssal plains and continental margins occur across broad zones of gradually changing seafloor gradient. Sediment-covered basin floors typically extend outward from continental rises before giving way to steeper margin topography. The boundary between plain and margin is expressed as a shift from low-relief expanses to inclined surfaces associated with continental slopes. In many ocean basins, abyssal plains terminate at the base of continental rises. These rises form gently inclined regions that separate flat basin floors from steeper continental slopes. The change in gradient is distributed over wide areas rather than marked by a sharp line. Sediment cover often continues across this transition zone, maintaining surface continuity despite increasing slope. The spatial extent of plain-to-margin transitions varies among basins. In the Atlantic Ocean, wide continental rises create gradual shifts between basin floors and continental slopes. Parts of the Pacific margin display narrower transition zones, where flat plains approach more abrupt slope gradients. Indian Ocean margins include both broad and relatively confined transition regions, depending on basin geometry. Sediment-covered expanses remain the defining characteristic on the basin side of these transitions. As the seafloor approaches continental margins, surface gradients increase, while overall sediment coverage persists across much of the rise. Elevated relief features may occur locally, yet the dominant pattern is one of gradual morphological change. Across global ocean basins, plain-to-margin transitions represent consistent structural relationships between expansive abyssal floors and adjacent continental edges. These transitions contribute to the large-scale organization of sediment-covered seafloor regions. Intrabasin low-relief sectors occupy central and peripheral portions of many ocean basins. These areas are characterized by broad sediment-covered surfaces with minimal variation in gradient across large distances. Their topography appears uniform in regional bathymetric datasets. Within individual basins, low-relief sectors may extend between major structural features, such as mid-ocean ridges and continental rises. These sectors often form contiguous fields that connect multiple abyssal plains. Localized elevations and fracture zones may intersect the basin floor, yet wide intervals retain relatively even surface profiles. The Atlantic Ocean contains several intrabasin low-relief regions on both sides of its central ridge system. Comparable sectors occur in the Indian Ocean, where sedimented basin floors span large central areas. In the Pacific Ocean, low-relief regions are distributed across northern and southern basins, separated by elevated plateaus and ridge complexes, while maintaining extensive cumulative coverage. Sediment thickness across these sectors contributes to the smoothing of smaller-scale irregularities. The resulting morphology is dominated by laterally continuous expanses rather than abrupt topographic contrasts. These areas frequently represent the most spatially extensive components of their respective basins. Across global ocean basins, intra-basin low-relief sectors form a consistent structural element of seafloor topographic features. Their distribution reflects the large-scale arrangement of basin interiors, where sediment-covered plains define broad horizontal domains of the ocean floor. Mapping surveys identify these sectors as extensive acoustic backscatter regions with limited relief contrast. Many extend across thousands of square kilometers without major topographic interruption. In several basins, adjacent low-relief sectors merge to form expansive composite plains. These regions remain a dominant spatial component of abyssal basin floors across multiple oceans. Abyssal plains and basin floors are frequently segmented into distinct sectors by linear and elevated features. These segmentation patterns divide otherwise continuous sediment-covered expanses into separate topographic compartments. The divisions are commonly expressed as subtle changes in gradient or as boundaries aligned with ridge systems and fracture zones. Within a single ocean basin, multiple abyssal plains may be arranged in parallel or offset configurations. Elevated ridges and plateaus can separate adjacent plains while maintaining comparable surface characteristics across each sector. The resulting pattern consists of broad, low-relief fields interspersed with elongated structural boundaries. In the Atlantic Ocean, abyssal plains are distributed on both sides of the central ridge system, forming paired sectors across the basin floor. The Indian Ocean contains segmented plains divided by intersecting ridge complexes and basin highs. The Pacific Ocean displays extensive compartmentalization, where numerous plains occupy discrete regions separated by ridge chains and volcanic plateaus. Sediment-covered surfaces often remain internally uniform within each segmented sector. Boundaries between sectors are typically gradual at large scale, though they correspond to distinct structural alignments in regional mapping data. The spatial arrangement of these segments contributes to the overall mosaic structure of ocean basin floors. Across global seafloor topography, plain segmentation patterns reflect the partitioning of large sedimented expanses into organized regional units. These patterns define how abyssal plains are distributed across basin interiors while preserving their characteristic low-relief morphology. Mid-ocean ridge systems form a continuous network of elevated seafloor structures extending across multiple ocean basins. This network traces long linear paths through the Atlantic, Indian, Pacific, and Southern Oceans. Ridge crests define the central alignment of these structures, creating a globally connected system of submarine mountain chains. In the Atlantic Ocean, the Mid-Atlantic Ridge extends in a north-south orientation through the central basin. This ridge forms one of the longest continuous ridge segments in the global ocean. Similar ridge alignments occur in the Indian Ocean, where several interconnected ridges form a branching configuration across central and southern basins. The Pacific Ocean contains an extensive ridge network composed of multiple segments separated by fracture offsets. These segments form long linear structures that intersect and diverge across the basin floor. In the Southern Ocean, ridge systems connect major ocean basins through a series of curved and segmented alignments. Fracture offsets divide ridge crests into distinct sections, while preserving the overall continuity of the global network. Individual ridge segments may extend for hundreds of thousands of kilometers before encountering lateral displacement along fracture zones. When mapped at planetary scale, mid-ocean ridge systems form a nearly continuous band of elevated seafloor terrain. This global ridge network represents one of the most extensive structural patterns present in seafloor topographic features. Additional ridge segments occur at junctions where multiple ocean basins meet. Several ridge intersections form triple junction regions, linking different ridge branches. Large-scale bathymetric maps display long chains of ridge crests aligned across basin interiors. Many ridge segments follow gently curving paths, rather than straight lines. Some sections are arranged as parallel ridge strands, separated by narrow troughs. Across the global seafloor, these ridge alignments collectively define an interconnected structural framework spanning the major ocean basins. Ridge crests form the central structural lines of mid-ocean ridge systems across global seafloor topography. These crests extend as elongated elevated ridges that trace continuous or segmented paths through multiple ocean basins. Their alignment defines the primary orientation of ridge systems at regional and global scales. In many areas, ridge crests follow long linear or gently curving trajectories that extend for hundreds to thousands of kilometers. These alignments often remain consistent across large portions of a basin before encountering fracture offsets. At these offsets, ridge segments shift laterally while maintaining the overall direction of the ridge system. The Mid-Atlantic Ridge presents one of the most recognizable crest alignments, extending from the Arctic Ocean toward the Southern Ocean. Along this path, ridge crests maintain a generally north-south orientation, with intermittent lateral displacements. In the Indian Ocean, ridge crest alignment forms a branching network where multiple ridge segments intersect and diverge across basin interiors. Across the Pacific Ocean, ridge crest alignment appears in long segments that trend across central basin regions. These segments are separated by fracture offsets that displace crest positions while preserving the continuity of the ridge network. Several ridge crests form linked chains that extend across large distances through the Pacific Basin floor. Axial valleys commonly follow the crest line along many ridge segments. These valleys appear as elongated depressions aligned with the central ridge axis. Their orientation generally parallels the crest alignment across extended portions of ridge systems. At global scale, ridge crest alignment contributes to a continuous pattern of elevated seafloor features, connecting multiple ocean basins. This alignment establishes the structural framework that defines the layout of mid-ocean ridge systems within seafloor topographic features. Axial valleys form elongated depressions that follow the central axis of many mid-ocean ridge crests. These valleys appear as linear troughs extending along ridge segments across multiple ocean basins. Their alignment generally parallels the orientation of the ridge crest, producing a continuous axial feature along substantial portions of ridge systems. The geometry of axial valleys varies along different ridge segments. Some valleys appear as narrow linear depressions bordered by steep inner ridge walls. Other segments display wider troughs, where the axial floor extends across broader sections of the ridge crest region. Despite these variations, the valley remains aligned with the crest axis along large distances. In the Atlantic Ocean, axial valleys are prominently expressed along the Mid-Atlantic Ridge. Long segments of this ridge contain clearly defined central troughs that trace the crest alignment from north to south. These valleys form a recognizable component of ridge morphology across extensive portions of the Atlantic Basin. Axial valley configurations in the Indian Ocean occur along several ridge branches that intersect across the basin floor. Individual valley segments extend along crest lines and are frequently offset by fracture zones that displace adjacent ridge sections. Similar arrangements appear along Pacific ridge segments, where axial valleys occupy the central position within elongated ridge structures. Fracture offsets interrupt the continuity of axial valleys at regular intervals along many ridge systems. At these locations, valley sediments shift laterally, while maintaining parallel orientation to adjacent ridge crests. The displaced sediments remain aligned with the overall structural direction of the ridge network. Across global mid-ocean ridge systems, axial valley configurations define a consistent structural feature associated with ridge crests. Their linear form and repeated alignment across multiple basins contribute to the characteristic topography of ridge-centered seafloor terrain. Ridge flank gradients describe the sloping surfaces that extend outward from the crest regions of mid-ocean ridge systems. These gradients form the transitional terrain between elevated ridge crests and the broader basin floors of the surrounding ocean basins. On bathymetric maps, ridge flanks appear as extensive inclined surfaces that descend gradually away from the central ridge axis. The gradient of ridge flanks varies across different ridge systems and along individual ridge segments. Some flanks display relatively steep slopes near the crest before transitioning to more moderate inclines farther from the axis. Other regions show broader gradients that extend across wide lateral distances from the ridge crest toward adjacent abyssal plains. Across the mid-Atlantic ridge flanks extend laterally from the crest into the surrounding Atlantic basin floors. These slopes define the elevated ridge structure against the lower basin terrain on either side. The gradient may change along the ridge length, though the general pattern of outward sloping terrain remains consistent. In the Indian Ocean ridge systems, flank gradients occur along multiple ridge branches that intersect across the basin interior. Each ridge branch presents paired slopes extending from the crest region toward adjacent basin sectors. Similar flank configurations are present along Pacific ridge segments, where extensive slopes connect crest structures with surrounding seafloor terrain. Fracture offsets intersect ridge flanks at intervals along many ridge systems. These offsets divide flank surfaces into segmented blocks aligned with displaced ridge segments. Despite these interruptions, the overall pattern of outward sloping terrain from ridge crests remains recognizable along extended sections of ridge systems. Across global seafloor topography, ridge flank gradients define the lateral extent of ridge structures and establish the transition from elevated crest regions to lower basin floor surfaces. Transform offset segments appear where mid-ocean ridge crests are laterally displaced along fracture zones. These offsets divide continuous ridge alignments into separate ridge sections that are shifted relative to one another across the seafloor. In regional bathymetric mapping, transform segments are visible as linear corridors connecting adjacent ridge crest segments. Each transform offset links the end of one ridge segment to the beginning of another segment that lies laterally displaced along the ridge system. The connecting corridor forms a narrow band of seafloor between the two crest sections. Along this corridor, the ridge axis does not continue in a straight line, but shifts sideways before resuming its previous orientation. Transform offset segments occur repeatedly along many ridge systems across the Atlantic, Indian, and Pacific Oceans. On the mid-Atlantic ridge, numerous transform offsets interrupt the north-south ridge alignment at regular intervals. Each offset produces a step-like arrangement in the ridge crest pattern across the basin. In the Indian Ocean ridge network, transform segments connect multiple ridge branches that intersect across the basin interior. Several offsets occur where ridge segments meet at different orientations. Similar patterns appear in the Pacific Ocean, where ridge systems contain numerous lateral offsets between crest sections distributed across the basin floor. Fracture zones commonly extend outward from transform offsets far beyond the ridge crest region. These zones appear as long linear features that continue across basin floors on both sides of the ridge system. Their alignment often matches the orientation of the transformed sediment connecting adjacent ridge crests. Across global mid-ocean ridge systems, transform offset sediments contribute to the segmented structure of ridge networks. The repeated lateral displacement of ridge crests forms a characteristic stepped pattern along many sections of the global ridge system. Mid-ocean ridge systems are divided into multiple ridge segments, separated by fracture offsets along the ridge axis. These divisions create intervals between adjacent ridge crest sections that form a repeating pattern along the length of ridge systems. The spacing between these segments defines the segmentation intervals observed across many ridge networks. Individual ridge segments may extend for tens to several hundreds of kilometers before encountering a lateral offset. At these offsets, the ridge crest alignment shifts sideways and continues along a parallel orientation. The distance between successive offsets establishes the length of each ridge segment within the overall ridge system. Segmentation intervals vary across different ridge systems and even along different portions of the same ridge. Along the Mid-Atlantic Ridge, many segments occur in relatively irregular intervals separated by well-defined fracture offsets. These offsets divide the ridge crest into a series of aligned but laterally displaced segments that extend through the Atlantic Basin. In the Indian Ocean, ridge segmentation occurs along several interconnected ridge branches. Each branch contains multiple ridge segments, separated by transform offsets that interrupt crest continuity. The intervals between these segments differ depending on the orientation and arrangement of the ridge branches across the basin floor. The Pacific Ocean ridge systems also display numerous segmentation intervals across extensive ridge alignments. Long ridge segments alternate with offset sections where fracture zones displace the crest line. These repeating intervals create a patterned arrangement along large portions of the Pacific Ridge network. Across global mid-ocean ridge systems, ridge segmentation intervals contribute to the structured layout of ridge crests and fracture offsets. The repeating spacing between ridge segments forms a characteristic organizational pattern within seafloor ridge topography. Isolated seamounts occur as individual elevated structures rising from the surrounding ocean basin floors. These features appear as discrete topographic highs separated from nearby seamount groups or ridge systems. In bathymetric surveys, isolated seamounts are identifiable as singular elevations located within otherwise broad basin regions. Many isolated seamounts are distributed across the Pacific Ocean basin, where numerous individual peaks rise from abyssal plains and basin floors. Some occur at considerable distances from major ridge systems or continental margins. Their spatial separation distinguishes them from clustered seamount chains and volcanic ridge alignments. In the Atlantic Ocean, isolated seamounts also appear across basin interiors and along peripheral basin sectors. These features often stand apart from nearby ridge structures, forming solitary elevations within large sediment-covered regions. Individual seamounts may occur hundreds of kilometers from other comparable features. The Indian Ocean basin contains several isolated seamount occurrences distributed across central and southern sectors. These seamounts appear as distinct peaks within wide basin floors that otherwise display relatively low relief topography. Their positions often contrast with nearby abyssal plains or sedimented basin expanses. Isolated seamounts vary in height and base diameter, but maintain recognizable conical or dome-like forms in bathymetric mapping. The surrounding seafloor typically slopes upward toward the summit from multiple directions. This geometry produces a clear topographic contrast between the seamount and adjacent basin terrain. Across global seafloor topography, isolated seamount occurrences represent a widely distributed component of ocean basin morphology. Their scattered arrangement across basin interiors contributes to the diversity of seafloor topographic features found between major ridge systems and continental margins. Linear seamount chains appear as a lined series of submarine peaks extending across sections of the ocean floor. These chains consist of multiple seamounts arranged along elongated paths that may continue for hundreds or thousands of kilometers. In regional bathymetric mapping, the peaks form recognizable sequences of elevated structures separated by intervals of lower seafloor. Individual seamounts within a chain are typically spaced along a shared directional trend. The alignment may follow a straight or gently curving trajectory across basin interiors. When viewed at basin scale, these chains form linear corridors of elevated terrain rising above surrounding abyssal plains and basin floors. The Pacific Ocean contains numerous examples of extensive seamount chains distributed across central and western basin regions. Some chains extend across large portions of the basin, with individual peaks appearing at regular or irregular intervals along the alignment. These chains often cross wide sediment-covered areas of the seafloor. Linear seamount chains also occur in the Atlantic and Indian Oceans, though they are generally shorter and less numerous than those in the Pacific Basin. In these oceans, chains appear as aligned groups of seamounts extending across sections of basin floors or adjacent volcanic rises. Guyots are frequently present within linear chains alongside conical seamount peaks. These flat-topped features appear as elevated plateaus positioned along the same linear alignment as surrounding seamounts. Their inclusion within chains contributes to the variety of summit forms observed along these sequences. Across global seafloor topography, linear seamount chains represent a distinct pattern of submarine elevation aligned across basin interiors. Their repeated arrangement forms recognizable structural corridors within seamount and guyot fields distributed throughout the world's oceans. Guyots are submarine elevations distinguished by their flat summit surfaces and steep flanks rising from surrounding basin floors. In bathymetric surveys, these structures appear as plateau-like tops positioned above the broader seafloor. The summit platform contrasts with the sloping sides that connect the flat surface to the adjacent ocean floor. The summit areas of many guyots extend across several kilometers and form relatively even surfaces when compared with nearby seamount peaks. These flat-topped forms are commonly surrounded by circular or elliptical outlines visible in regional mapping data. The summit edge typically marks a transition from the horizontal plateau to descending flank slopes. Guyots are widely distributed across the Pacific Ocean basin, where large numbers of these structures occur within seamount fields and linear chains. Many appear in clusters or alignments, extending across central basin regions. Their presence contributes to the variety of summit geometries observed among submarine elevations in the Pacific. In the Atlantic and Indian Oceans, guyots occur less frequently, but remain present within several seamount provinces. These features appear as isolated flat-topped elevations, or as components of aligned seamount groups across basin interiors. Their summit platforms often stand above surrounding sediment-covered plains. The flank slopes of guyots descend from the plateau margins toward adjacent basin floors in multiple directions. These slopes form a continuous transition between the summit platform and the surrounding seafloor terrain. The summit surface itself remains relatively level compared with nearby conical seamount peaks. Across global seafloor topography, flat-topped guyot forms represent a recognizable class of submarine elevation. Their plateau-like summits and steep surrounding flanks distinguish them from other seamount morphologies found within seamount and Guyot fields. Seamount cluster regions consist of multiple submarine elevations located in relatively close spatial proximity across sections of the ocean floor. These regions contain groups of seamounts that appear together within defined areas of basin terrain. In bathymetric mapping, clusters are visible as concentrated fields of elevated peaks rising above surrounding seafloor surfaces. Individual seamounts within a cluster vary in height, base diameter, and summit shape. Some peaks display steep conical profiles, while others show broader dome-like forms. The spacing between neighboring seamounts may range from a few kilometers to several tens of kilometers, creating a dense arrangement of submarine elevations across the cluster area. Large seamount cluster regions occur across several Pacific Ocean basin sectors. In these areas, dozens or even hundreds of seamounts appear within extensive fields distributed across basin interiors. The peaks rise from surrounding abyssal plains or basin floors and form complex topographic landscapes of closely spaced elevations. Clustered seamount fields also occur in the Atlantic and Indian Oceans, though they generally occupy smaller spatial regions than those found in the Pacific. These clusters appear as groups of submarine peaks located across volcanic rises or basin floor sectors. Their distribution often contrasts with nearby areas where the seafloor remains comparatively uniform. Guyots may occur alongside conical seamounts within cluster regions, adding variation in summit morphology across the field. Flat-topped falls appear interspersed among peaked elevations, creating mixed summit profiles within the cluster. Across global seafloor topography, seamount cluster regions represent concentrated zones of submarine elevation distributed within basin interiors. These clustered fields form recognizable provinces within broader seamount and Guyot fields across the world's oceans. Seamounts and guyots exhibit a wide range of vertical dimensions relative to the surrounding basin floors. These submarine elevations rise from the ocean floor with varying summit heights, creating a spectrum of size categories observable in bathymetric surveys. The height of each structure is measured from the surrounding seafloor to the summit surface. Some seamounts rise only several hundred meters above nearby basin terrain. These smaller features appear as modest topographic highs within broader abyssal plains or basin floor regions. Their bases may extend laterally across several kilometers while maintaining relatively limited vertical relief. Intermediate seamounts display greater vertical extent, often reaching heights of 1 kilometer or more above the surrounding seafloor. These structures form prominent peaks within seamount fields or isolated basin locations. Their slopes extend upward from the basin floor toward a defined summit or plateau. The largest seamounts and guyots rise several kilometers above adjacent seafloor surfaces. These major submarine elevations dominate local topography across extensive sections of basin terrain. Their bases may span tens of kilometers while supporting large summit regions near the top of the structure. Guyos frequently occupy the upper portion of the larger height categories. Their flat summit platforms occur at elevations significantly above surrounding basin floors. The plateau surface typically contrasts with the steep flanks that descend toward the deeper seafloor around the base. Across global seafloor topography, height range categories illustrate the diversity of submarine elevations present within seamount and Guyot fields. A variation in vertical scale contributes to the complex relief patterns observed across many ocean basin regions. Seamount and Guyot fields display substantial variation in the spatial density of submarine elevations across different ocean basin regions. In some sectors of the seafloor, numerous seamounts appear concentrated within relatively small geographic areas. In other areas, individual peaks are widely separated by large expanses of basin floor terrain. High-density seamount regions contain large numbers of closely spaced submarine elevations distributed across limited spatial domains. In these areas, bathymetric mapping reveals clusters of peaks, occurring within tens of kilometers of one another. The surrounding seafloor appears densely populated with individual seamount summits rising above the basin floor. Lower density regions show a contrasting spatial pattern. Individual seamounts, or guyuts, may occur at intervals of several tens to hundreds of kilometers apart. These isolated peaks stand above extensive sediment-covered plains or basin floors that display comparatively few elevated structures. The Pacific Ocean contains several regions of high seamount density, particularly across central and western basin sectors. Numerous seamount fields occupy wide areas of the basin interior, producing complex landscapes of closely spaced elevations. In contrast, other Pacific regions display broader spacing between individual seamounts. In the Atlantic and Indian Oceans, seamount density varies across different basin provinces. Some sectors contain small cluster regions where multiple peaks occur in proximity, while neighboring areas may contain only scattered, isolated seamounts. These variations produce uneven spatial distributions of submarine elevations across basin floors. Across global seafloor topography, spatial density variations contribute to the structural diversity of seamount and guyut fields. Differences in the number and spacing of seamounts shape the visual patterns observed in bathymetric representations of ocean basin terrain. Major oceanic plateau regions form extensive elevated provinces across several ocean basins. These plateaus appear as broad areas of seafloor standing above adjacent basin floors. Their surfaces often extend across hundreds of thousands to millions of square kilometers, creating some of the largest elevated domains within oceanic topography. Several prominent plateau regions occur across the Pacific Ocean basin. The Ontom Java Plateau represents one of the most expansive submarine plateaus, occupying a vast area in the western Pacific. The Shatsky Rise and the Manihiki Plateau also form major elevated provinces distributed across central and western Pacific sectors. These plateaus display wide summit surfaces that contrast with surrounding abyssal plains. In the Indian Ocean, the Kerguelen Plateau forms another extensive oceanic plateau region. This elevated province stretches across a large portion of the southern Indian Ocean basin. Nearby rises and plateau fragments appear across adjacent sectors of the basin floor, forming additional elevated regions within the same broad oceanic domain. The Atlantic Ocean contains fewer large plateaus, but includes several volcanic rises and elevated plateau-like regions distributed along basin margins and interior sectors. These structures appear as broad topographic highs rising above neighboring basin floors. Their surfaces may contain smaller ridges, seamounts, and elevated plateaus within the larger rise region. Oceanic plateaus typically exhibit relatively broad and gently undulating surfaces compared with narrow ridge crests. Their edges descend towards surrounding basin floors through gradual slopes or escarpments. The plateau margins define the boundary between the elevated province and adjacent abyssal terrain. Across global seafloor topography, major oceanic plateau regions represent large-scale elevated domains distributed across multiple ocean basins. Their expansive surfaces and distinct elevation above basin floors establish them as prominent components of oceanic plateau and rise systems. Regional oceanic rises appear as broad elevated areas that extend across large sections of ocean basin floors. These rises form expansive topographic highs with gently inclined surfaces that stand above surrounding abyssal plains. Their boundaries are commonly expressed through gradual transitions rather than abrupt escarpments. Oceanic rises occur in multiple ocean basins and vary widely in spatial extent. Some rises occupy large portions of basin interiors, while others appear along basin margins or adjacent to major plateau regions. Bathymetric mapping typically shows these rises as wide areas of elevated terrain containing subtle relief variations across their surfaces. In the Atlantic Ocean, several regional rises extend outward from basin interiors and continental margin regions. The Rio Grande Rise in the South Atlantic forms a broad elevated province located between South America and the Mid-Atlantic Ridge. Nearby elevated features create additional rise regions across sections of the basin floor. The Indian Ocean contains several prominent rise formations, including the Mascarene Plateau and adjacent elevated regions extending across parts of the basin interior. These rises form wide topographic highs with gently undulating surfaces that contrast with deeper basin floors surrounding them. Across the Pacific Ocean, large rise structures also occur within basin interiors and near plateau provinces. Some rises appear as expansive domed regions, supporting scattered seamounts and diates across their surfaces. These elevated areas occupy significant portions of the seafloor relative to nearby abyssal plains. Regional oceanic rises often contain internal topographic variation, including ridges, small plateaus, and isolated seamounts distributed across the rise surface. Despite this variation, the overall structure remains an elevated domain relative to adjacent basin terrain. Across global seafloor topography, regional rise formations represent widespread elevated provinces distributed among oceanic plateau regions. Their broad extent and moderate elevation above basin floors contribute to the large-scale relief structure of ocean basins. Oceanic plateau boundary margins mark the transition between elevated plateau surfaces and the surrounding ocean basin floors. These margins define the outer limits of plateau provinces across the seafloor. In bathymetric mapping, plateau boundaries appear as zones where the broad summit surface gives way to descending slopes toward deeper basin terrain. Plateau margins often extend across large distances along the edges of major oceanic plateaus. The boundary zone may consist of gradual slopes, stepped escarpments, or combinations of both forms. These features outline the perimeter of the plateau and separate the elevated interior surface from adjacent abyssal plains or basin floors. The Ontong Java Plateau displays extensive boundary margins along its outer edges across the western Pacific Basin. These margins descend from the broad plateau surface towards surrounding deep ocean terrain. Similar margin structures appear around the Shatsky Rise and other Pacific Plateau provinces. In the Indian Ocean, the Kerguelen Plateau also exhibits well-defined boundary margins. These margins trace the outer edges of the plateau, where elevated terrain transitions toward deeper surrounding basin floors. Nearby plateau fragments and rises display comparable boundary structures across the region. Plateau boundary margins frequently contain smaller ridges, escarpments, and slope variations distributed along the edge of the plateau surface. These features contribute to the irregular outline that often characterizes the perimeter of large plateau regions. In some locations, seamounts and diates occur along the plateau margins as additional elevated features near the boundary zone. Across global seafloor topography, plateau boundary margins form an important structural component of oceanic plateau and rise systems. These margins define the limits of plateau surfaces and establish the spatial separation between large elevated provinces and adjacent ocean basin floors. Oceanic plateaus and rises vary considerably in their horizontal extent across the ocean floor. Surface area classifications describe these elevated provinces according to the size of the region they occupy on the seafloor. In bathymetric mapping, The lateral boundaries of each plateau or rise define the total surface area covered by the elevated terrain. Some plateau regions occupy extremely large areas that extend across substantial portions of ocean basins. These expansive provinces cover hundreds of thousands to more than 1 million square kilometers of seafloor. Their broad surfaces form extensive, elevated domains rising above surrounding abyssal plains and basin floors. Intermediate-sized plateau regions occupy smaller yet still substantial areas within ocean basins. These plateaus may extend across tens of thousands to several 100,000 square kilometers. Their surfaces form broad, elevated platforms that remain clearly distinguishable from adjacent basin terrain. Smaller plateau fragments and rise structures occur across many ocean basins as localized elevated areas. These features may occupy several thousand square kilometers or less. Despite their smaller surface extent, they maintain the general characteristics of plateau or rise topography relative to the surrounding seafloor. Oceanic rises also exhibit variation in surface area. Some rises extend across wide regions, comparable in size to smaller plateaus, while others appear as moderately sized elevated provinces within basin interiors. Their surface areas are defined by the boundaries separating the rise from deeper surrounding basin floors. Across global seafloor topography, the classification of plateau and rise surfaces by area provides a way to distinguish among the wide range of elevated provinces distributed across ocean basins. Differences in lateral extent contribute to the diverse scale of plateau and rise features observed throughout the world's oceans. Plateau, ridge adjacency zones occur where broad oceanic plateaus lie in close spatial proximity to mid-ocean ridge systems. These zones represent regions where large, elevated plateau surfaces approach or connect with elongated ridge structures across the seafloor. In regional bathymetric mapping, the adjacency appears as a transition between wide plateau terrain and the narrower crest alignments of ridge systems. Several plateau regions occur near major ridge networks across the Pacific Ocean basin. The Shatsky Rise lies adjacent to segments of the Pacific Ridge System, where elevated plateau surfaces occupy areas near ridge-aligned terrain. The proximity between these structures creates extended zones in which plateau margins and ridge flanks appear within the same regional topographic setting. In the Indian Ocean, plateau ridge adjacency is visible near the Kerguelen Plateau and surrounding ridge systems. Portions of this plateau approach nearby ridge alignments across the basin floor. The surrounding seafloor shows broad, elevated plateau terrain located close to elongated ridge structures extending through the basin interior. Adjacent relationships between plateaus and ridge systems may also occur near smaller rise provinces distributed across ocean basins. In these areas, plateau edges lie near ridge segments separated by moderate distances across the seafloor. Bathymetric mapping often shows gradual topographic transitions between plateau surfaces and ridge-related terrain. Within plateau, ridge adjacency zones, additional features such as seamounts, ridges, and escarpments may appear across the transitional region. These features contribute to a varied topographic landscape where broad plateau surfaces and ridge structures occur within the same geographic sector of the ocean floor. Across global seafloor topography, plateau, ridge adjacency zones represent regions where two major structural elements of ocean basins occur in close spatial relationship. These zones illustrate the geographic proximity of large plateau provinces and extensive mid-ocean ridge systems across several ocean basins. Oceanic plateaus and rises occur at a variety of elevations relative to surrounding basin floors. Elevation range groupings describe how these broad submarine provinces occupy different vertical levels across the ocean floor. In bathymetric mapping, the height of a plateau or rise is measured as the difference between the plateau surface and the adjacent abyssal terrain. Some oceanic plateaus occupy the highest elevation ranges among large submarine provinces. These plateaus rise several kilometers above neighboring basin floors and display extensive elevated surfaces across wide regions of the seafloor. Their summit areas stand prominently above surrounding abyssal plains, producing large-scale topographic contrast across basin interiors. Intermediate elevation groupings include plateaus and rises that occupy moderate vertical positions above the basin floor. These elevated regions rise noticeably above adjacent terrain, but do not reach the highest elevation levels observed among the largest plateau provinces. Their surfaces form broad elevated domains distributed across several ocean basins. Lower elevation groupings include rise structures that extend only modestly above surrounding basin terrain. These rises appear as gently elevated areas with gradual slopes that transition toward nearby abyssal plains. Although their vertical relief is smaller, their horizontal extent may still cover large areas of the seafloor. Within many plateau provinces, internal elevation variation also occurs across the plateau surface. Some portions of a plateau may stand higher than surrounding sections, forming smaller elevated subregions across the broader plateau domain. These variations contribute to the complex relief patterns visible in bathymetric representations of plateau surfaces. Across global seafloor topography, elevation range groupings illustrate the differences in vertical scale among plateaus and rises distributed throughout the world's oceans. These variations in elevation contribute to the diversity of large elevated provinces across ocean basin terrain. Major oceanic trenches form long, narrow depressions that trace extensive alignments across the margins of several ocean basins. These trench systems appear in bathymetric mapping as elongated troughs extending for thousands of kilometers along ocean basin boundaries. Their alignments define some of the most continuous linear depressions present on the global seafloor. Several major trench alignments occur across the Pacific Ocean basin. The Mariana Trench extends in a long arc across the western Pacific, forming a continuous depression adjacent to island arc systems. Nearby trenches, including the Tunga and Kermadec trenches, follow similarly elongated alignments across the southwestern Pacific region. The Peru-Chile Trench forms a major trench alignment along the eastern margin of the Pacific Ocean. This trench extends parallel to the South American continental margin for a considerable distance across the southeastern Pacific basin. The Middle America Trench follows a comparable alignment along the margin of Central America and southern Mexico. Additional trench systems occur along the margins of the western Pacific basin. The Japan Trench, Kurile, Kamchatka Trench, and Philippine Trench each form long linear depressions adjacent to island arc regions. These trench alignments extend across broad sections of the basin margin and appear as continuous troughs in regional seafloor mapping. In the Indian Ocean region, several trench and trough systems occur along basin boundaries and arc-adjacent regions. These depressions follow curved alignments that trace the margins of island arcs and adjacent oceanic domains. Their spatial arrangement contributes to the structural complexity of trench systems in the region. Across global seafloor topography, major trench alignments represent extensive linear depressions distributed along ocean basin margins. Their long, continuous form distinguishes them as prominent components of trench and trough systems within oceanic topographic features. Oceanic trenches vary widely in their total linear extent across the seafloor. Trench length categories describe how these elongated depressions differ in the distance they extend along ocean basin margins. In regional bathymetric mapping, The length of a trench is measured along the continuous alignment of its central trough. Some trench systems extend for several thousand kilometers and form some of the longest continuous depressions on the ocean floor. These long trench alignments trace broad arcs along the margins of ocean basins. The Peru-Chile Trench and the Kuril-Kamchatka Trench represent examples of extensive trench systems that continue across large geographic distances. Intermediate-length trenches occupy shorter but still substantial sections of basin margins. These trench systems may extend for many hundreds to more than 1,000 kilometers. The Japan Trench and the Mariana Trench fall within this range of trench length, forming prominent linear depressions across portions of the Western Pacific Basin. Shorter trench and trough systems occur along limited segments of ocean basin boundaries, or arc-adjacent regions. These depressions may extend only a few hundred kilometers before transitioning into adjacent trough systems or merging with other seafloor features. Marginal troughs along island arc regions commonly display these shorter length ranges. Some trench systems consist of multiple connected segments that together form a longer overall alignment. In bathymetric surveys, these segments appear as adjacent depressions, separated by subtle structural breaks along the trench axis. When viewed at basin scale, these segments form extended trench systems across the seafloor. Across global seafloor topography, trench length categories illustrate the variation in horizontal extent among oceanic trenches and troughs. Differences in total length contribute to the diverse patterns of elongated depressions distributed along ocean basin margins. Margin parallel trough systems appear as elongated depressions that extend along the edges of ocean basins adjacent to continental margins or island arc regions. These troughs follow linear or gently curving alignments that trace the boundary between basin floors and margin-related topography. In bathymetric mapping, the trough axis commonly runs parallel to the adjacent continental or arc margin over long distances. Many margin-parallel trough systems occur along the margins of the Pacific Ocean basin. The Peru-Chile Trench and the Middle America Trench both follow extended alignments that track closely alongside continental margins. Their trough axes maintain a consistent orientation relative to the adjacent coastline and basin boundary. Additional examples appear along island arc margins, where elongated troughs parallel the arc alignment. The Japan Trench and the Kuril-Kamchatka Trench extend along the margins of arc systems across the northwestern Pacific Basin. These troughs display curved paths that mirror the broader shape of the arc systems nearby. Margin-parallel trough systems may extend continuously for hundreds or thousands of kilometers along basin edges. In many regions, the trough alignment remains relatively consistent, even where the surrounding seafloor terrain varies in elevation. The trough axis commonly maintains a narrow, elongated form throughout its length. Several trough systems also occur along the margins of smaller oceanic basins and marginal seas. These troughs trace basin boundaries in a similar parallel orientation relative to adjacent arc or continental structures. Their presence contributes to the structural definition of many basin margins. Across global seafloor topography, margin-parallel trough systems represent a common geometric pattern among trench and trough features. Their alignment along basin edges creates long linear depressions that follow the general orientation of nearby continental or arc margins. Oceanic trenches and trough systems frequently display segmented arrangements along their overall alignment. These segmentation patterns divide long trench depressions into multiple connected sections distributed along basin margins. In bathymetric mapping, the trough axis may appear continuous at basin scale, while still consisting of distinct segments separated by subtle structural breaks. Individual trench segments often extend for several hundred kilometers before transitioning into adjacent sections. The boundary between segments may appear as slight changes in trough orientation, localized ridges crossing the trench axis, or offsets in the alignment of the trench floor. These features create visible divisions along the length of the trench system. Across the Pacific Ocean basin, many major trenches exhibit segmented structure along their margins. The Japan Trench and the Kuril, Kamchatka Trench, both contain multiple trough segments that follow curved alignments along the basin edge. Each segment maintains a similar orientation, but may shift slightly relative to neighboring sections. Segmentation patterns also occur along trench systems in the southwestern Pacific region. The Tonga and Kermadec trenches extend along island arc margins, while displaying several distinct trough segments along their overall length. The alignment of each section contributes to the broader arc-shaped geometry of the trench system. Marginal trough systems in smaller ocean basins may also display segmentation along their axis. These troughs may contain shorter segments connected across gradual transitions in the seafloor terrain. The divisions between segments are commonly visible in detailed bathymetric surveys of basin margins. Across global seafloor topography, trench segmentation patterns represent a recurring structural characteristic of long oceanic depressions. The arrangement of multiple connected segments forms extended trench systems distributed along the margins of ocean basins. Trench basin adjacency regions occur where elongated trench depressions lie directly beside broad ocean basin floors. These regions mark the spatial boundary between narrow trench troughs and the extensive surfaces of adjacent abyssal plains. In bathymetric mapping, the trench axis forms a linear depression positioned immediately next to the wider basin terrain. Along many Pacific Ocean margins, trench basin adjacency appears as a sharp transition between the trough floor and nearby basin surfaces. The Mariana Trench borders large sectors of the western Pacific Basin floor, where the trench depression lies adjacent to wide abyssal plains. Similar spatial relationships occur along the Tonga and Kermadec trenches in the southwestern Pacific region. The Peru-Chile Trench forms another prominent trench basin adjacency zone along the southeastern Pacific margin. The trench alignment runs parallel to the basin floor of the eastern Pacific, creating a continuous boundary between the narrow trench depression and adjacent deep ocean terrain. The Middle America Trench displays a comparable spatial arrangement along the margin of Central America. Across the northwestern Pacific Basin, several trenches lie beside large basin floor regions. The Japan Trench and the Kuril, Kamchatka Trench both form elongated depressions located adjacent to expansive sections of Pacific Basin terrain. These trenches trace the outer edges of basin floors while maintaining parallel alignment along the margin. Marginal trough systems in smaller ocean basins also display trench basin adjacency patterns. These troughs lie alongside basin floor regions within marginal seas or arc-adjacent domains. Their depressions define narrow corridors bordering broader seafloor terrain. Across global seafloor topography, trench basin adjacency regions illustrate the close spatial relationship between major trench systems and the large basin floors of ocean basins. These regions define the boundary between elongated trough depressions and extensive deep ocean terrain. Oceanic trenches and trough systems display a wide range of depths relative to surrounding ocean basin floors. Depth range classifications describe how these elongated depressions vary in vertical position across different trench systems. In bathymetric mapping, trench depth is measured from the surrounding seafloor down to the lowest portions of the trough floor. Some trench systems occupy the greatest depth ranges found in oceanic topography. These trenches extend far below nearby basin terrain, and form some of the deepest depressions on the seafloor. The Mariana Trench and the Tonga Trench represent examples of trench systems that reach extreme depths relative to adjacent basin floors. Intermediate depth ranges occur in many trench systems distributed along basin margins. Trenches such as the Japan Trench and the Kuril-Kamchatka Trench form deep troughs that extend significantly below surrounding seafloor surfaces, though they do not reach the deepest recorded values among global trench systems. Their trough floors remain distinctly lower than nearby basin terrain. Other trench and trough systems occupy more moderate depth ranges relative to adjacent seafloor. Marginal troughs in some arc-adjacent regions descend below nearby basin surfaces, but display smaller vertical differences compared with the deepest oceanic trenches. These depressions appear shallower when compared with the largest trench systems. Depth variation also occurs along the length of individual trench systems. Certain segments of a trench may contain deeper sections, separated by areas of slightly higher trough floor elevation. Bathymetric mapping commonly reveals a series of localized depth variations distributed along the trench axis. Across global seafloor topography, depth range classifications illustrate the variation in vertical scale among trench and trough systems. These differences in depth contribute to the diverse relief patterns present along ocean basin margins. Across the world's oceans, the seafloor forms a vast network of plains, ridges, plateaus, seamount fields, and trenches distributed across every basin. These large-scale structures define the underlying topographic framework of the ocean floor. Their arrangement continues across the global seafloor as a connected landscape extending far beyond any single region.